Hey guys, welcome back to another video. In this video, we're going to talk about enthalpy change of solution and hydration, both of which are new concepts. So let's start off with enthalpy change of solution. What is the definition of enthalpy change of solution? By the name, you might already think of dissolving an ionic compound or a compound in water and form a solution. So it's similar to that. So specifically, if we talk about enthalpy change of solution, by definition, it is the enthalpy change when 1 mole of an ionic substance dissolves in sufficient water to form a very dilute solution. In a lot of cases, it will be mentioned as an infinitely dilute solution. Infinitely dilute solution. Therefore, enthalpy change of solution is basically the process when you take 1 mole of an ionic compound and try to dissolve it in excess water, meaning it is forming an infinitely dilute solution or a very dilute solution where all of the solid has dissolved. That is why we write it as very dilute solution, because until and unless all of the solid or ionic substance has dissolved, you're not going to get the accurate value or accurate change in enthalpy. Because if you're doing the experiment, you're not going to get the accurate rise in or fall in temperature. Great. The symbol AQ means enough or sufficient water, and once it is dissolved in excess water, we add the symbol AQ. So a few examples of enthalpy change of solution could be taking MgCl, adding water, AQ, and forming the ions Mg2 plus AQ plus Cl minus AQ. So you can write it separately like this, or you can write it together as MgCl AQ, both of which means the same thing. Because MgCl aqueous means they're existing as Mg2 plus and Cl minus AQ. Great. Now, one thing to remember is enthalpy change of solution can be both endothermic and exothermic. You may think that since the bond is broken or dissolved, the ionic compound is broken and dissolved, so it must be endothermic since bonds are broken. But no, there is an exothermic process as well where bonds are formed, and we are going to look into that, which is why the enthalpy change of solution can vary, can be more endothermic or more exothermic. So enthalpy change of solution actually takes place in two parts, in two steps for that matter. First, the ionic substance, the solid or the lattice structure, is first broken down, meaning it is the reverse process of enthalpy change of lattice energy of formation. It is the reverse process of lattice energy of formation. In formation for lattice structure, what we saw is electrostatic forces of attraction was formed to form an ionic compound. In this case, the reverse process is happening. Therefore, energy in this case is not going to be released. It's going to be gained because the bonds are going to be broken. So, reverse of del H lat. Therefore, endo. So in this case, the breaking of lattice is the endothermic process, and it is the first step. Next, what happens is that those broken parts or the ions, the gaseous ions, because the lattice energy talks about forming gaseous ions into an ionic substance. The reactants for lattice energy of formation was gaseous ions. So if in case of formation, it was gaseous ion. In case of breaking it down or breaking the lattice structure, it's going to be giving you gaseous ions as well. So after you've broken the lattice structure, you get gaseous ions. Great. Now, enthalpy change of hydration. What is enthalpy change of hydration? It is basically the bonds formed between the ions, let's say Na plus and Cl minus. These ions, gases by the way, since the lattice structure is broken. So these gaseous ions form a bond with the water molecules. These bonds are given the name ion-dipole force, meaning that if we look into these examples, you can see that there are bonds between, let's say in case of positive ion, it forms a bond with the negative end or negative pole of the water molecule and forms a ion-dipole bond or force. Therefore, even in case of the anion, it's going to form a bond with the positive part of the water molecule, which has the positive charge or the positive poles, meaning the hydrogen ions. So the chlorine ion will form a bond with the hydrogen ions. This is called ion-dipole attraction or force. And this formation releases energy. This formation is going to release energy, and this becomes the enthalpy change of hydration, where ion-dipole forces of attraction are formed between water molecule and the gaseous ions. So these are the two steps in which the entire solution happens. The entire enthalpy change of solution happens in first, the lattice structure is broken, then the ions, the specific ions, the let's say sodium and chloride ions are hydrated. After they're hydrated, the entire process of solution has happened. Great. So by definition, what is enthalpy change of hydration? It is the standard enthalpy change where enthalpy change of hydration is the change in energy when 1 mole of a specific gaseous ion dissolves in sufficient water to form a very dilute solution. Again, very dilute or infinitely dilute solution, whichever you want to write. So what is happening? 1 mole of a gaseous ion, let's say sodium ion, 1 mole of sodium ion will dissolve in sufficient water to form a very dilute or infinitely dilute solution. Great. An example, Mg2 plus aqueous, water, and forms Mg2 plus aqueous. This is the process of hydration. It might look quite similar to the first equation where it was enthalpy change of solution. But remember, in enthalpy change of solution, your starting product is the ionic solid, and the ending product is the aqueous compounds. In case of hydration, you're starting off with the gaseous ions and ending with aqueous ions. Great. So what is the formula of enthalpy change of solution? Enthalpy change of solution is given by minus enthalpy change of lattice energy of formation, this, and plus enthalpy change of hydration. Now, why is there this odd minus sign in front of the enthalpy change of lattice energy? In your question paper, it's going to give you the values as, let's say, for NaCl, let's say, the del H lat is going to be given by minus, let's say, 1000, an arbitrary value. All right, kilojoule, 100 kilojoule per mole. Let's say this is given in the question paper. Now, you know, in the case of enthalpy change of solution, it's not going to form the ionic structure. It's going to break it. So it's not going to be minus 100. It's going to be positive 100 since those exact bonds are going to be broken down. Therefore, we have to add a minus sign, because if you plug in this exact value, you don't need to change anything. You plug in this exact value and the minus will get cancelled out. The minus will get cancelled out and you get a positive 100 value, which is why we add a minus sign. That is the whole reason of adding a minus sign in front of del H flat, because we want the positive value. Why do we want the positive value? Because it's an endothermic process in the case of enthalpy change of solution, where the ionic structure is broken off. Great. So the equation can be written as enthalpy change of solution is minus del H flat plus del H hydration. If you plug in the values for del H flat or del H hydration, you will get the enthalpy change of solution. Now, as I've already mentioned before, enthalpy change of solution can be both endothermic and exothermic. Why? Let's say del H flat, which is in this case the endothermic process or the dissociation. So in this case, it's going to be a positive enthalpy change. So it's going to be endo. Considering the minus sign is going to be endo. So the greater the value of enthalpy change of lattice, the more endothermic del H solution is going to be. If the hydration is small and del H flat is greater, the del H solution is going to be more endothermic, since the del H lattice energy is giving you a more positive value. So the net value or for del H solution, it's going to be more endothermic. Similarly, if we talk about the reverse process or the opposite case, since del H hydration is always exothermic, if it is really large exothermic value, if it's extensively exothermic, and del H flat is more or less somewhat endothermic considering the minus sign, the entire value for del H solution is going to be far more exothermic. Why? Because the enthalpy change of hydration is really large. The enthalpy change of hydration is really large, for which the entire value for del H solution becomes more exothermic. Great. So this is how the del H flat and del H hydration affects or influences if or not del H solution becomes endothermic or exothermic. Great. So next we can explain enthalpy change of solution in a few steps. I've already shown you the example, but you can go over this again and understand how the bonds are formed. So first of all, in case of breaking the lattice, the water molecules comes up and with their dipoles, water molecules basically have dipoles, two poles, the positive and negative end. So these water molecules will form a sort of attraction with the positive and negative ions. Let's say the negative ion is chlorine, the positive ion is sodium, and it's going to form a sort of attraction with those ions. After forming those attractions, these are going to be strong enough to separate them from the ionic structure, and they become free. Remember, they are still not aqueous. Even though there was sort of bond between them, force of attraction, those were only enough to break the bonds or take them out of the ionic structure. Those were not enough to hydrate them. Next up, after these form gaseous ions, you can hydrate them. So what happens in the hydration process? The potassium ion is going to get all the oxygen ends of the water molecule and is going to attract those poles of the water molecule and form ion-dipole attraction or ion-dipole forces. As a result, potassium ion gets hydrated since these bonds or forces of attraction are formed. Similarly, in case of chloride, it will attract the positive hydrogen ions and form ion-dipole force. Great. Now, for enthalpy change of solution and hydration, you can draw a Hess cycle. How do you do that? You know, enthalpy change of solution happens in how many steps? 2 steps. Great. So what is the direct step? The enthalpy change of solution itself. If you're given the value of enthalpy change of solution, you can directly get the value. Let's say in this case it is minus 100. So you know it's an exothermic process. And you know the direct value or the enthalpy change from the direct route. Great. So what is the indirect route? It can be broken down into how many steps? 2 steps. You take the ionic solid and dissociate it. You break the lattice structure and form ionic gas. So del H lat, but dissociation, not formation. So you are forming gaseous ions. Great. After you do that, you can hydrate those gaseous ions and form aqueous ions. And this is going to be the second step where you're hydrating the gaseous ions. So in this case, route 1 is the direct route, enthalpy change of solution. Route 2 is the indirect route where it's dissociating and then hydrating. Great. So in this way, you can break down the enthalpy change of solution and use Hess cycle or Hess law to find out any specific variable, be it hydration, dissociation, or solution. Now, in question papers, it may be represented differently. Alright, so I found an example of the case where they use the ionic gas as the starting set of reactants. In my case, I started off with the solid, and in this case, they're starting off with the ionic gas. So what they're doing is, this entire process is del H hydration, where they first hydrate the potassium ion and then they hydrate the chloride ion. So first what they do is they hydrate it and they get the ionic aqueous solution. Alright, and the other end, this one end and the other end is enthalpy change of solution, the direct enthalpy change of solution, where what they're doing is they've given the total value, which is endothermic in this case, plus 26 kilojoule per mole, and they're taking the ionic solid and directly dissolving it and getting the solution, the aqueous solution, and this is del H solution. So from the ionic gases, they do hydration and get to this solution. The other is where they directly dissolve the compound and get this solution. Now, what is this? This is enthalpy change in forming the lattice structure. So how do you get the direct and indirect route in this case? What you do is, you know, this is the starting point. The direct would be this. The indirect would be this. Sorry. The direct would be this and the indirect would be this. So the direct one in this case has 2 steps and the indirect one has 2 steps as well. So you basically take lattice energy and enthalpy change of solution on one side, and you take both the hydration energy on the other side, right? And then you make whichever you want to calculate for the subject. So let's say you don't know, in this case, lattice, the enthalpy change of formation for the lattice structure. In this case, you can write del H L plus del H S is equals to del H height of K plus del H height of Cl minus. So from this, you know minus 322, and you know minus 363, and you know solution which is plus 26, plus 26. So from this, you will get, if you make del H lat the subject, you get the value for lattice energy of formation. Great. So in this case, in this way, you can make any variable the subject, and as long as you're clear about the direction of the arrowheads, you can calculate and get any variable, get the enthalpy change for any variable. Great. So for me, this is definitely much more simple and easier to understand, since I know there are two steps happening. First is dissociation and then hydration, and that is easier for me to keep in my mind. So if I have to draw, I'll probably draw it like this. But in a lot of question papers, they can sort of overcomplicate it and write in this form using the arrowheads. So yeah, you might have to be used to these diagrams if you're asked to calculate for lattice energy or hydration or solution. So next we can move into what else? Right. So it can be del H solution can be either endo or exo, depending on the amount of energy released for hydration and the amount of energy taken in for breaking the lattice structure. So it depends on both of those. So yeah, for del H solution, if it is really exothermic or only slightly endothermic, the salt will dissolve in water, meaning the salt is water soluble. So if it is much more exothermic, it's supposed to be much more soluble. Great. So for factors affecting the enthalpy change of hydration, there are the common two factors. One is radius, the ionic radius, and the ionic charge. Right. So for enthalpy change of hydration, what is the factor? Since it's an exothermic process, we are talking about attraction, forces of attraction. So we are trying to see in which case there is greater amount of attraction and in which case there is weaker amount of attraction. Therefore, what are the two factors, common factors? A, the charge. B, the radius. Usually the first priority is the charge, the ionic charge. So let's look into that at the beginning. So if the ion has a greater amount of charge, best believe the amount of energy released when it is getting hydrated will be much more. Therefore, del H hydration is much more exothermic if the ionic charge is larger, since the charge density is going to be larger, because within the same amount of volume or area, there is a greater amount of charge, so the charge density increases. So that there is a stronger ion-dipole interaction or force formed. Therefore, when forming the bonds, more energy is released. Great. So that is the case for ionic charge. For ionic radius, what happens is, if the radius is smaller, let's say in both cases, the charge is +1 and +1. One is huge, one is small. For the huge one, the +1 charge is distributed over a larger area, making the charge density far smaller. In case of the smaller radius, the charge density is higher, since that +1 charge is distributed over a smaller area. Great. So del H hydration is more exothermic if the ionic radii is smaller, meaning charge density is greater, giving you stronger ion-dipole attraction. So as a result, more energy released when forming the bonds if the radius is smaller. Great. That's it for hydration and solution, enthalpy change of hydration and solution. Next, we can look into a few examples and a few question papers.